All right, Dave, whenever you're ready.
Okay, great. Thanks. Thanks so much, Mark. My name's Dave Intner, welcoming everyone to this AIA-supported webinar that SCE is providing, instructor support and topics in a series that we'll have through the end of the year related to energy and decarbonization. The first two in the series are going to be taught by Ed Dean, who I'll introduce in a moment, the author of a couple of case study books that we supported the development of. And then the remaining two in the series are called Code Breakers, and they are a deep dive into topics related to the energy code in California in partnership with our program that we support called Energy Code ACE. One is going to be on all electric and zero net carbon design, single family designs, and then finally we'll do a code breaker on accessory dwelling units. So today's session, as well as two of the remaining three, will qualify for zero net carbon design CEUs, which I know many of you will need for your relicensure either in the current cycle or can carry over the next one if you've already had your birthday. But we'll go ahead and introduce today's session and note that today's session is being recorded. So if you want to go back and watch anything, it should be up on the AIA website and or YouTube within the next day or so. Inviting folks to provide questions you may have in the chat, and we will try to periodically address those over the course of the presentation, or depending on how many there are, we may hold some till the end. So without further ado, let me go ahead and introduce today's speaker. Ed Dean has been a longtime champion of low energy, sustainable building design for his entire career, which has included practice at major firms including EHDD, NBBJ, ZGF, and SOM. He led the design team for the West Branch Library for the City of Berkeley that was certified ZNE in 2015 by the International Living Future Institute, achieved LEED Platinum certification, and was selected in 2016 as one of the AIA Committee on the Environment Top 10 projects. Ed is now engaged in full-time consulting practice with his own firm, Burnham and Dean Incorporated, in sustainable and healthy building design and ZNE design in particular. Ed is the author of a series of case study books on net zero energy and zero net carbon, which SCE has supported the development of. These two presentations, the one today on non-residential, and then the following one in, I think it's in a week and a half or 2 weeks on multifamily residential, are the two most recent, and that's what we're going to be highlighting. And I will provide links to where you can find those case studies online in the chat. So without further ado, I'd like to turn it over to Ed. Thanks, Ed.
Oh, thanks, Dave. I am going to share my screen now and get started. Okay, shared screen, play from start. All right, there's the start of the presentation. Welcome to everybody, and glad to have you on board about this particular project.
Internet working? Okay.
Oh, okay. I thought that was a verbal question. This 1 hour talk is we're going to present 3 case studies that were out of the 5 in the book that you see there on the screen, Designing for Carbon. I'll show you more about this book in just a second. But we're going to take 3 of the case studies that were done for the book and discuss them in some detail.
Ed, it looks like you just went on mute. I don't know if you can unmute yourself.
Yeah, I wonder
there
why
you go.
Okay, sorry. Where was I when I went mute? You know,
you were just introducing the case study books.
Okay, then it just happened. And I'm quick on it. Bear with me. I'm just getting started and a little fidgety. Okay, so I've been working on these case study books for about 9 years, thanks to the California Public Utilities, of which Southern California is an is been the most interested and most supportive. The one we're talking about today, 3 case studies, are from this book in the middle on the top. It shows the office building in San Diego that we are going to talk about as the first case study. But all of these books are available for free as a PDF online. It's a public service. And you can see at the very top of this slide the URL. That's going to be in the chat if you want to copy it. You can download all of these books for free and examine all of the detail of the case studies in that. So that's the information, the background information, the context of this webinar. Plunging into webinar, we're going to, the contents of today's talk is first an introduction to how we're going to structure each case study, simply because we're going to do each one in about 15 minutes. The first study is going to be that speculative office building in San Diego that you saw a picture of. This case study 2 is going to be a public school, which is an interesting topic very currently. And both of them are new buildings. And the third one is going to be a renovation study. And we're going to touch on embodied carbon analysis in that case study. So let's get going with the introduction. Just want to list what topics we're going to talk about in each case study. We give the background, but mostly we're most interested in the zero carbon design strategies. Then renewable energy sources that are were able to be installed in each project. Then, most interestingly, in some regard, is the analysis, both energy and carbon, and the actual performance with real data. Nothing like real data to see if your assumptions in the model were correct. And then at the very end, we want to make very candid observations about the projects and the useful lessons learned. So let's plunge right into the first case study. You can see it's a new building. It's 6 stories at a ground floor level of retail spaces, and there's rentable office space in the 5 floors above. This is, as I said, in San Diego. Here is the, I'm going to try to move this bar there. Okay. It's the tenant leases for this building. The client, it's an interesting story. There was a competition for a developer team and architects, and it was won by Langford and Associates as the managing partner. It was an invited competition in 2014. The project was actually completed in 2018, and the winning team of architects with Langford was BNIM of San Diego, and mechanical engineers were Siska Hennessy of San Diego. And one of the reasons they were selected, they won the competition, was they wanted to try to get a zero net energy design, at least to cover the common spaces of the building. And also they wanted to do all electric design, so that ultimately when California's grid goes all decarbonized in 2045, as currently scheduled, the building will be zero carbon operating at that time. So that sold the owners of the land, and they were awarded the design. This is the site. It's in a part of San Diego called the Makers Quarter. You can see outlined here in red. This area was where artists did their work in warehouses, and there were little factories, and basically it was known as the Makers Quarter. And the land was bought by a family called named Navarro, had a small business there, and they developed it since the days of the Depression accumulating property and became owners of the property down here. They own the land. The developer has land lease, which had some implications for the planning. You can read about the details of all this in the case study. As I said, you can be downloaded for free in the PDF. First, it came a housing project, and then Block D, which is outlined in yellow, was the project site for the office building. And as I said, the zero carbon goal was a factor in both obtaining the initial financing and in the team winning the project. This is a typical floor plan. The San Diego Planning Code does count outdoor balconies as assignable space. So the designers developed the idea of indoor-outdoor tenant spaces with natural ventilation that's fundamental to the use of the space. This is, remember, San Diego, they have perfect climate year-round, so they can do something like that. But the control system integrates the garage doors, which you can see in plan and also in the photograph here. When the doors are open, the control system makes sure that the heating and cooling system cannot come on. If you want the heating and cooling system to operate either in a hot summer day or in the middle of winter, then all the doors and windows have to be closed. That's a requirement. And the tenants are given instructions about this when they lease the space. And also the tenants have to show any improvements they want to make to the space and get it approved by the owners, because sometimes it could interfere with the airflow in the building. So they have to approve the tenant improvement. What's interesting here is that the sides of the building are responsive to the sun control. See the west side there are these sliding metal screens that the tenant can move at will if they're occupying the balconies, making workspace out there, either meeting spaces or so forth. But on the south side, they have blinds which move down into place and automatically tilt in response to the sun's position. So it maximizes daylight at the same time it's protecting the glass. Here's a picture of that. You can see actually letting the sun in this case for the photograph, but it's all automatic operating tilting of the blinds. As I say, it optimizes daylight. Now the mechanical cooling is really needed there in San Diego, but the building is heated and cooled by a single heat pump. It has multiple zone fan coil units connected to VRF lines, variable refrigerant flow lines. So there's not a big air handling unit on top of the building, as has been typically the case for the past decades. And each floor has its own dedicated outdoor air supply. When the garage doors are closed and the windows are closed, and you're operating cooling, you have to introduce fresh air. So there's a dedicated outdoor air supply, which has an energy recovery heat exchanger for it. So every smart feature has been introduced in this building. And it's really worth looking at the details. Again, look at the details and download the PDF and look at it quite carefully. There's a lot of lessons to be learned here. The kitchen, of course, since the building is all electric, the kitchen on the tens has to be all electric. So that's just appliances and so forth. There is a ground floor coffee shop, a retail space. So they have to make electric cooking down there. And that's very, very feasible to do. What's interesting here, this is a roof plan that shows that solar panels in place. Luckily, since there's not all air handling units on the top by design, you can put the solar panels up there but there is some equipment, and so therefore the solar panels are elevated above the equipment, and you can see it here. And in the area around the edge of the roof on the west and the south sides, there are bifacial solar panels, so that light can be captured from below underneath the panel, as well as from the sun hitting the top of the panel. And there's a picture of this in the next slide right there. You can see the panels kind of going right out to the property line above the roof, and they're collecting light, sunlight from above, and the diffuse light from below, and increasing the amount of solar collection possible. So the building was modeled, the energy use was modeled, and also was measured. When this case study book was done, they had just collected data for the first year or two, and this shows when the first big tenant moved in, major tenant moved in 2019. You can see the energy jump when a tenant got in there. The common area is there in gray, and the light blue is the energy used by the tenant. But still, the modeled AUI is almost double what the actual measurement was. But that of course is because the first part of the year there wasn't using much. It looks like there's going to be it's going to be just about correct that the model and measured for a typical year is about the same. And the solar, as you can see here, let me take a minute and explain it. The solar collected by the PV system is the orange curve, and the energy use by the common area, the core and shell, is the solid black line. So the PV energy, the solar energy collected is greater than the core and shell energy use. So it can be stored, it can be sent back on into the grid. When the tenant's energy use is added on, the building use is obviously much higher. For a 6-story building, you'd have to have an enormous field or microgrid somewhere if you want to make it zero energy. But in this case, they accomplished what they wanted. And summary in this case, did they achieve project goals? Yes, they had zero net energy, which was a principal goal at the time of the design of this project. They achieved it for the core and shell areas. Financial goals, it turns out, to not bring the gas onto the site and do all the plumbing necessary to route it everywhere. You said they saved a lot of money, and they found that these zero carbon, zero energy features also save money in terms of the cost of the operation. So that the financial goals were achieved, what they analyzed and what they achieved. The commissioning challenges were as you can imagine, with new systems, or at least systems that are not commonly used in buildings. You have to make sure that you commission this carefully, make sure they operate. Otherwise, there's going to be complaints and bad reputation about this all electric building with these fancy bells and whistles that don't work, So you have to commission, spend time and do careful commissioning. In this case, the commissioning was done and they all worked quite well. One thing I'll note is the embodied carbon, they didn't do an embodied carbon assessment, which is now on the agenda of firms who are doing projects like this to do. And it wasn't done then because it was being designed at a time when the tools were not really available or common, and it wasn't understood. The importance of it wasn't quite understood. And now it's a little bit different. And the design team said they do it now as part of their regular project work. So I don't have something to show you on the embodied carbon, but that's coming up. So Dave, if any urgent question that we can answer before we plunge to the second case study?
I didn't see anything in the chat. If anybody has a burning question on the first case study that they want to quickly come off mute and ask, we can address it now. Otherwise, we can certainly come back around at the end.
Okay. Yeah, I'll just plunge on.
Yep.
Maybe we can.
I don't see any hands raised or anyone jumping in. So yeah, let's go ahead and continue on. And again, if you have questions, folks, put them in the chat and we'll try to address them as we go.
And I'll probably say this too often, but again, it's in the case study. The details of these buildings and the design of these buildings is in the free PDF version. Recommend downloading it. So let's talk about a school. This is a middle school added to a site in the city of San Francisco. So this is up north, as I say, the original school. It's a typical middle school in the public school district in San Francisco. San Francisco has developed some design standards for, at the time, was zero net energy, and certainly now is all electric, zero carbon design for all future projects. In this case, there was a 12,000 square foot addition of only classrooms and a gym, a large gym, and a two-story building onto the existing campus. Let me show you a picture. It's over near the Marina District of San Francisco, so it's near the northern waterfront. You can see the building there in the middle of the site, occupying about 2/3 of a city block. And to the north of the yellow circle, you can see bungalows, which was typical of when they didn't have room, they just put bungalows on the site and put classrooms there. There's an old building, existing building, I think it was from the 1930s or 1920s even, there on the edge of the block, just outside the circle. So that was the school that they were adding this new middle school to. And they put it on the playground area, and right there. The neighbors, of course, had neighbor meetings, and neighbors didn't want their view of the bay to the north blocked. So they made an agreement with the city that there would be nothing on the roof that would stick up. So that kind of actually one of the advantages of the all-electric buildings with heat pumps. They put the heat pumps on the ground in this case, and they didn't have package units up on the top here. And that was the agreement with the neighbors, that they would not put junk on the top of the building, including including those solar panels that annoyingly stick up above the roof. So it had an impact on the solar design for the project. They couldn't put it on the edge of the block. On the street, you couldn't put equipment or solar panels there. As I say, the city of San Francisco had developed design standards in a general way. They'd run models of schools in different locations, and this project was actually selected to test the design standards. There was a bond measure passed that gives you some sense of the time scale involved in this. The bond measure, $500 million of school construction was passed in 2011. Now, more than 10 years later, they are building those buildings, but it took a long time to develop the building. This building had an RFP issued in 2016 as a bungalow replacement project. They decided to apply these new design standards to it as a test, and I think it was finished in 2019. So the idea of how much time is taken to complete these projects. The design standards, as I said, they wanted to be all electric, so it would be zero carbon in 2045. Again, the common motivation. Here's a site plan that shows the new building and the bungalows to the north. The bungalows, I think, may have been removed at this point. And the whole thing taken over by the schoolyard. As I say, it's two wings of classrooms and one large gymnasium. Here's a building envelope design. They built it with metal studs, so therefore they did apply rigid insulation over the metal studs to prevent the thermal bridging that would occur and greatly reduce the insulating value of the envelope. So keep that in mind on any building project that you're doing. If you're using metal studs, by all means, get the rigid insulation covering it, so you're not bridging, giving a heat flow path to the outside. And you can see also in the picture, they have manual windows. That's the natural ventilation. So natural ventilation, well insulated. And the daylight control, that the sunshades you can see on the left, they provide shade. At least when this photo was taken, the time of year, at least partially shaded to reduce the glare as well. And the gym has a kind of cowl wall skylight at the top, and a way to diffuse the daylight so it's not too glaring for people using the gym. And the heating system, as I mentioned, there's a excuse me, a ground-mounted electric variable refrigerant flow heat pump with conventional vertical fan coil units in each classroom. By requirement in the city of San Francisco, only heating is provided, no cooling at all in the climate. So that's fine. They still have a heat pump, even though they could turn it into cooling if they wanted to. There's only a roof-mounted heat pump package unit for the gym. It's the only thing on the roof besides the solar panels where they could put them that sticks up above the roof. They decided for cost reasons to go with an electric resistance hot water heater. And here's the roof plan. You can see that in the lower left wing of the building, there's a standard roof. That's to satisfy the neighbors, by the agreement with the neighbors. But it's funny that they put a gabled roof on the front that provided a screen for the solar panels on the inside roof, which is kind of a clever thing, I guess. And the panels are all over the gym roof, except where the heat pump package units are. Somehow they got away with putting panels on the gym roof on the street edge. Yeah, design issues, design constraints. Sometimes there are things that come from the outside, and you have to deal with them, as you well know, probably. This was what the modeled EY was at 13 kBTU per square foot per year, and this one advancing. It actually was measured electric use. What happened? This project also had issues in 2019 when it was finished. They barely occupied it when they shut down for the pandemic, and no one's going to school anymore. So they didn't even install the solar panels by then. Their plan was to, I think it's in place now, just recently put on the roof of the building. Third-party PPA installed a PV system. But this orange curve is the energy production according to the model with the energy production. And you can see that the calculated EUI of being the actual data collected it shows it's using a little bit more than it's being produced according to the model. So that is yet to be seen if it's going to be zero energy or not. It will be zero carbon operationally in 2045. And that was the goal. And they learned, the city of San Francisco Unified School District learned a lot from this project in terms of future school projects. So that's all good. So did they achieve the carbon goals? as I say, the school closed in 2020 and only recently reopened. So they're now collecting real data, actual data, and they'll soon see if they are doing close to their goal. Design centers have been informed by it, and now they're into the spending all that bond money on schools. And what'll really be interesting is to see how some of those schools are designed and themselves are functioning. As future reports on the schools will be very informative. Again, the embodied carbon assessment wasn't done because, again, the analytical tools that were available were not as good and as useful to architects. Let me put in the word for Lionakis Architects. I think I forgot to mention that they were the architects of record on this in this case, and Capital Engineering was the engineer. Sorry about that. Yeah, so embodied carbon assessment again was not done for this case, but for the final case study, a renovation, in fact, embodied carbon analysis was an important feature. Even though it was done more or less at the same time as the other two projects, it was designed with an engineering firm that was very interested in embodied carbon, and therefore they took it upon themselves to do the analysis. Before I start that, though, Dave, are there any questions?
So I received one question on the first case study, but I thought maybe we could address it here because it is actually one that could be relevant to the second as well. And it was one related to the question of how you handle ventilation when you have a VRF system. And since both projects we've looked at so far had VRF, I think it's maybe worth noting, did both of these projects that you're aware of have a dedicated outside air system to couple with the VRF in order to provide that ventilation? And were there any noted benefits on the decoupling of those two systems, space conditioning from ventilation, from an energy standpoint? And how did all that work with the natural ventilation measures that both projects had in terms of mixed mode?
Well, the project in San Diego clearly was designed around that natural ventilation, and the doors, as I mentioned, they had to be closed, and all the windows had to be closed. And if the system wasn't operating, cooling or heating, the tenants had to figure out what window was open in the space. That's something they had to live with. But there was, in that case, a DOAS system providing the fresh air. So the tenants, interestingly, that building filled up. They leased out early because everybody was interested in all the advanced features of the building and saving energy and zero carbon and so on. And so they got tenants who were motivated to learn how to operate their own spaces, and that was kind of unique too. The school was more of a conventional school. The teachers and students had to operate the windows. I'm going to take a chance here and let me open my case study book here, so I'm not flipping through the slides. The question was, is there a DOAS system? I don't want to also going to spend too much time on this.
Yeah, and while Ed's looking that up, it's a good opportunity to note that you can actually get physical copies of these. They're available basically for the printing cost through Amazon. If you prefer not to look at it on a screen and want to, purchase a copy directly. We also have some copies we give out at events. So if you're at the Net Zero conference, that's a little plug, on the 13th, downtown LA, we'll have some copies of the latest volume to give out there. But yeah, there's the opportunity to have a physical copy as well for those that just like that tactile experience of flipping through a book.
I don't have a report about a separated, if they close all the windows in the middle of winter during a time when they have to actually heat the classrooms. If there's a window left open, it sounds like they would still, the system would still come on. Yeah,
Okay.
there's a VRF system, but it doesn't say that there's a control system, which is that would be quite a stressful thing to put on the teachers to make sure the windows are closed and the system cooperate. I guess I would. I'm sorry. Anyway, that's my best answer, with short of reading the book. So I recommend again, get a free copy. Get it from Amazon. Amazon. If you Google designing
zero net carbon.
Zero carbon. It pops right up. In fact, you get about all three books together with that title. All right, so let's plunge into this renovation project. You see a picture of it right there. This one is at the Claremont College, Pitzer College, inland a little bit from Los Angeles and north. It's as it turned out, it became a renovation project of what was a former student infirmary of the Claremont colleges. They are turning it into a multi-use college classroom building. What's quite interesting is the well, there's a lot of interesting things about it. In 2012, Pitzer College established a new interdisciplinary academic program focusing on environmental issues, climate resilience, sustainability, and so on. It was kind of technically oriented, and so they wanted classrooms and laboratories to teach these things to college students who are majoring in that subject of environmental issues and so forth. They also wanted to have an outreach program to the local K-12 schools in environmental education, so they could come for a visit to this facility, and someone would take them through the labs and talk about environmental issues. They located it on a site which was a field station, old field station, still undeveloped, just north of the Claremont Colleges. So they called it a conservancy, this program. What was interesting to me, the building program ended up being 14,000 gross square feet, science lab and so on. And the existing building was only about 8,000 usable first floor space. So what's interesting how they got to the program total, you'll see in a minute. I want to say this is sorry, I'm just going to back one slide. Nope, I'm not. This is it's Carrier Johnson architects. I want to make sure I give credit to the architects. The mechanical engineers were integral group in Los Angeles office, and they were the ones who wanted to do the embodied carbon analysis. This started off as this feasibility study for the Claremont colleges. It included the building program, the construction cost estimate, energy modeling, and what Integral Group wanted to do, embodied carbon analysis, to look at the question of should we renovate this existing building on the site. And you can see it in the right here. It's kind of bordering a suburban developed area, and to the left in the bottom of this image is the field station belonging to the Claremont colleges. So it was built right on the edge. The existing buildings run on the edge of the property. So in 2015, Claremont Colleges did a feasibility study in which they looked at either renovating this building, even though it was smaller than the program, or building a new building on the site. They did the feasibility study. I'm going to show you what the results were. They selected that team to go ahead and build the building, design and build the building, obviously the construction. What you see here in this slide is the old photograph of the building from 1931 when it was built as a student infirmary, a student hospital. They had, it was funny, after the 1918 pandemic, they were very, and the lack of antibiotics generally, they decided that they would put student health facilities, student infirmaries away from the campus and put it in this field station so that they could quarantine students. So that's the way they dealt with like pandemic type things. They put the students in quarantine and in a separate building. But what happened in Claremont College, they closed the building in 1970s because they didn't functionally have any use to it. They wanted to demolish the building, but there was a local uproar about demolishing a building that everybody knew, and it was not registered on a historic site, but it was considered historic, and so Claremont College relented and decided not to demolish it. They just left it alone, and it gradually decayed, had animals living inside, and the doors fell off and so on. And that was the state in 2016 when the feasibility study was done. So they not only were deciding whether to use to renovate the existing building, they would have to completely refurbish the existing building. So it wasn't going to be cheap. The usual thing to do then was to just demolish it and build a new building. But to their credit, they did the feasibility study, and the college decided to save the building. So they did an embodied carbon analysis of the renovation versus new. This shows you the pie chart for the embodied carbon of the renovation. And if you renovate the project, you would still have to put new floor slabs, new roof decks, beams, and so on. So the biggest chunk is still those elements of the building. And when they also did the analysis with, let me see, sorry. Oh yes, the analysis was done, I should mention, with an early software package called One Click LCA. Was used the output from a Revit model, and then you use that software to do life cycle assessment. That's a word for embodied carbon analysis. It was called One Click LCA. Now the software is built into the Revit model, and it's called Tally. So it's much better these days. These days being 5 years later, but they did an early version of this analysis by Intergroup, showed the new building having quite a bit of embodied carbon compared to the renovation. So this was one of the factors that led the client to choose to do the renovation, because it would be lowering carbon. After all, they was in a building, the program of which was to study environmental issues and to be very scientific about it and sustainability and so on. So with this information, they decided we have to do the renovation, we have to try it. So then the problem became, how do we squeeze 14,000 square feet into 8,000? So you can see what one of the solutions was to utilize the unused basement space for some program. It turns out they got 2,500 square feet as a renovation of the basement space. There underneath these classrooms is a crawl space, a traditional crawl space. So they couldn't do that, but the basement space is right under the center of the building. And then they decided to add 3,500 square feet of outdoor classrooms, which again was appropriate for the program. and the outdoor classrooms were put under protective canopies, on the top of which they put all the solar panels. Because it was a historic building, they did not want to put it on the renovated building. They wanted the building to look the way it did in 1931. And so the solar panels went on top of these canopies that were the outdoor classrooms space. I don't know what happens when it rains a lot down there, whether they cancel classes for the day or whether they're out of the rain enough. I don't know. I didn't ask them that. But here, anyway, the building envelope, you can see where they had to insulate, again, because the outside of the building was to look like the old 1931 building. They had to insulate on the inside. The walls were poured concrete. So this is detail. They also replaced the windows, not the window frames, because they had to look like the old windows. They replaced the glass only with double pane units, and they have a radiant barrier up there in the attic, which they've super insulated. They did daylighting. The original building had one skylight above each of the classrooms in the classroom wing, and it's kind of like option one here. They decided they wanted the skylights were removed at some point between 1931 and 1970, and they wanted to restore the skylights, and they introduced daylighting. So they did these daylighting studies. Option one was like the original design. Option two was the two skylights over each classroom. And then option three was the double amount of skylights. And what they found was that option three was kind of glary, especially on sunny days. So they chose option two. And this is the way it looks inside, quite nice and quite airy and light. And ventilation, well, because it was the idea of the 1931 student infirmary, they wanted to let lots of fresh air in for the patients who would be in hospital beds there, who were sick with something that they couldn't really cure. So they had lots of ventilation. The whole building was designed originally with ventilation. Now, what they decided to do with the skylights was to make them operable and to make a path for the air to move through the crawl spaces underneath the classrooms and up through the skylights, naturally drafted. They didn't have a fan, except they had very slow-moving fans for those days when there was no air movement at all outside. So they get the ventilation, the air movement, and they use it at night to pre-cool the structure as much as they could. On warm days, it got cool enough at night that they would let air move in through the building. And they took a lot of broken pottery, a lot of broken pots that they found, stuck them in the crawl space, and it became like a thermal mass reservoir. So they used it as part of this mixed mode pre-cooling of the building. So I think they had fun coming up with these ideas and making it work. There are, again, fan coil units tied to a heat pump. Again, only they wanted to be really careful about only the windows can only be open if the heating and cooling system of the heat pump is not operating. So again, the control system, as soon as you open the window, the heat pump doesn't work. So that means you have to educate every year the new generation of students and teachers to this operational unique aspect. So because it's an environmental science building, it made sense to do it like this. If it were just like the tennis space we were referred to before, it probably doesn't. Well, they did in San Diego, but it maybe doesn't make sense for other applications. And I talked about the night flush operation. And this is a view of the outdoor classroom with the solar panels. and you can see it extends out, so maybe they can hold outdoor classes in a rainstorm, but maybe they have to cancel temporarily, or maybe there's a way to have a roll down screen. Anyway, it's one question I forgot to ask them. And this just shows the model versus the measured energy use. Modeled energy modeling always assumes average use, and maybe they were using the building very intelligently for this 1 year when they measured data, but it shows they're on track. And this is the energy production versus energy use. And for this case, you can see it is a performing zero net energy building for sure during this particular year. And were their goals achieved? Yes, they got all kinds of certification. They minimized embodied carbon. They met all the program goals. User involvement. I like the fact that everybody has to understand the building. It's a bit of a drawback in some ways if you look at it. There is no way to tell details about how the energy performance of the building is doing, and for a building of this type with the users who they are, providing feedback by submetering maybe in the classroom itself, like the energy use, or on a computer screen, energy use this month is such and such compared to normal, maybe a great interest to the students or the faculty. Anyway, this embodied carbon assessment, glad to say that this was successfully done and drove the decision to renovate the existing building, even though it was in a deplorable state of affairs, rather than build a new building at that particular site. So it was a successful project, that's for sure. Again, we said this about 10 times, but the free PDF is available at this website. And as Dave said, Amazon has softbound copies of these books, quite cheap by comparison to other books on a topic of zero carbon design. So check it out. With that, I'm going to turn it over back to Dave, or any questions maybe.
Yeah, so there were a few questions in the chat specifically related to embodied carbon. So maybe we can expand on that conversation a little bit. I did provide some resources in there, but the first question was asking about kind of what motivated the project team to embark on the embodied carbon analysis, and is there kind of a time and money impact on a project for doing that type of an analysis?
The engineering firm that did it is at the cutting edge. They're known to want to explore things. In 2018 or 2016, when the project was initiated, that's when the subject started to become hot. And these guys, as I say, were at the cutting edge, and they wanted to do it. Whether they charge, I don't know, whether they charge for it, or maybe it was lumped into their whole analysis fees. Maybe the client, I don't know the answer to the question that in that regard. I'm just surmising. Maybe the client who was really, really interested in the environmental study said, sure, do it, and they went ahead and did it. It was on the cutting edge. They used the early version of the software. Now all sorts of really interesting things are being done by many firms using the software that's now available.
Yeah, one thing I'd note there is, that the analysis only needs to be as detailed and as comprehensive as kind of you find useful information potentially. So for instance, you could start with just the big ticket materials. I think it's concrete, steel, and aluminum represent almost a quarter of total embodied carbon emissions from the built environment. So even if all you do is look at those materials and kind of ignore everything else, you're still going to have a significant impact if you can find ways to reduce embodied carbon in those areas for little investment. The other comment, I think, is you alluded to some of the tools that are now integrated into your workflow software tools. So you mentioned that Revit now has Tally as an option within its workflow. So you can leverage existing software tools you may already be using, and the inputs are already part of your BEM model, and just taking that module and kind of taking the next step are some options to kind of be able to provide some actionable design feedback without necessarily investing a lot of cost.
All right. I will say that in the subsequent book, which we're going to talk about on September 12th, the architects of one of the projects, Methuen, when we talked about the embodied carbon analysis they did for that project, it was interesting to me that what they use it for, they can put actual products that they're going to use into the model in great detail, and what they get back is if there's a hotspot, if a particular manufacturer and product has more embodied carbon than another, they can see it and they can identify the quote. They call it hotspots. So they use it rather than renovation versus new. It's not that discussion. For a new building, you're looking at specific products, and we want to minimize the embodied carbon in this, like a roofing material or something. The software will actually identify if you slip another manufacturer's product in there, its embodied carbon impact. So you can find these so-called hotspots, and that's what Methuen is using it for. I was quite taken by that one. It's interesting. So I encourage everybody to come back on September 12th and
great plug.
Hear about that one, because it's really, really interesting.
So there was another question you were talking about in existing buildings and embodied carbon. Kevin asks about, given the embodied carbon advantages of renovations compared to new buildings, are there any additional incentives to steer development towards renovation other than kind of the inherent savings on carbon that might be inherent to a renovation over a new building, and specifically policies and grants? And I guess I'd note here, and I'm noted it in the chat, but of course, the Building Standards Commission has approved CalGreen standards that are intended to go into effect next July that will put embodied carbon into code with mandatory requirements. They'll only be applicable to projects above 100,000 square feet initially. And there are multiple compliance pathways, and one of those pathways rewards the use of an existing building. So it's kind of an easy pathway if you happen to be able to use an existing building. And I know that where local jurisdictions are considering reach codes around embodied carbon or ordinances to encourage and promote embodied carbon analysis in projects, they're also looking at life cycle analysis, and reusing an existing building generally performs favorably in a life cycle analysis. I don't know if you have anything to add to that, Ed.
Several things occurred to me, but obviously other architectural things like does the program work for the client better in a new building versus an old building? If you really have to contort the program to work in an old building, obviously that's an argument for the client, for them to decide. But it will appear on the list of pros and cons, I think. It's more than just materials. A lot of issues there. Maybe it has some effect on the PV that you can put on the building. That's easier with a new building than with an existing building. Or in this case, it was historic, so they couldn't put anything on the existing building. You had to put it off on the site. Fortunately, they had site to put the panels on. So if you have car canopies for parking cars, you can put over a parking lot. Then you can keep the historic building looking the way it looks, and so on. So a lot of it is, as we know, dependent very much on the individual project and the individual client.
Great. Well, we're at time. So I don't see any additional questions, but very much appreciate everyone's time and attention today, and hopefully see everyone in a week and a half when we do our next, or 2 weeks, sorry, when we do our next version of this with the multifamily case studies, and encourage everyone to download the case studies, take a look, share them with your clients as opportunities to show, hey, we're talking about these strategies, but they've been done before, they're proven. Here's some successful projects that have utilized these strategies. So thank you all so much.
Thank you, Dave. Thanks, everyone.